Hello teacher, my name is Casey Company. Now I'll walk through the two algorithms that I implemented, the round robin and MLFQ. Starting with the round robin, um, the core idea is that each process gets a fixed time slice called a quantum, and they take turn. If a process doesn't finish within its quantum, it goes back to the end of the queue and waits for its next turn. Now in here, first thing the function does is that it violates the quantum, and if someone passes zero or negative number minimum, the minimum quantum and the remaining time would always return zero, meaning that the process executes for zero times, the current time never advances, and the loop runs forever. So I raise a value error immediately if the quantum is less than one. In here, and in here, I also decopy the process list before doing anything. This is the one of the most important part because we run multiple algorithms on the same input. So without the decopy, one algorithm would modify the process objects and interrupt the data for the next one. And around here, I use the Python collections DQ as the ready queue. It gives the O1 append and pop out both ends before the main loop starts. I feed the queue with any process that arrives at time zero. In here, I return the process runs the minimum quantum remaining time. So if the process only has one tick left, but the quantum is full, it runs for one tick and finishes. For here, after the process finishes its quantum, the first EQ any process that arrives during that slide and only then re-add the preemption process to the back. This matches the standard conventions where a process such as plan goes behind anyone who was already waiting. Reversing this order gives a complete different game path output and the different matrices. And now for the RFQ, RFQ here, instead of one queue, we have the three Q0 round robin with quantum 2 as the default, and Q1 round robin with quantum 4 default, and Q2 is the quick process. So one process, which is Q2, it runs to completion. So every new processes always enter Q0. Around here, if a process uses its full quantum in zero without finishing it, it gets denoted to Q0. If uses the full quantum in Q1, it drops to Q2. The idea is that the CPU intensive processes naturally sinks to lower queues while source processes finish quickly in Q0. Here I wrap each process in an RFQP process object that adds queue level and the weight field. This keeps the RFQ specific state completely separated from their processor class, so other algorithms are never affected. Mm, Here we apply the aging here, but the motion alone causes the starvation, so a process stuck in Q2 might never run if the Q0 and Q1 are never busy. So I implemented aging. Any process that waiting 10 or more ticks in Q1 and Q0 will get promoted one level up. In here, the apply agent function works like not sorting both queues into eligible by level first before moving anything. This means that the process in C2 that has waited for long enough moves to Q1 and stays there until the next aging checkpoint at most level of the promotion project. Here, same as the Robin also violates both Q1, Q0 and Q1 on the entry. A zero quantum animal Q is even more dangerous because the loop has multiple Qs and an infinite is much harder to debug. And now I'm gonna go through main a little bit more. So in here, finally look at the main. This is where the flag connects to the web interface to the algorithm function. And in here, the API run, routes, receive, or post requests from the browser containing the process with the selected algorithm and the quantum values. It converts the incoming JSON into the process object or the responding algorithm function. FC, FCFS, J, for job post, SRT, round robin, and MLSQ, and return the Gantt chart list and the matrix back to the JSON. And for in here, the API compare routes does the same thing, but it runs the 5 algorithms on the same inputs at once and return the average matrix for each, which is what the powers comparison table and the bar chart in the browser. And all the algorithms now modules imported at the top of CSS mod and so on, and the web interface temporarily implemented any figuring logic. It's just called these same functions in the terminal still unused. And now I'm gonna go through the web interface here. We have the three panels. On the left, we have schedule configuration and some timeline with the process table and the matrix performance on the right here. And in here we have options you can choose, and you can also load the file now. I'm gonna press the comfort zone with the process in here, and this is the default value. And for the birth time, I'm gonna put it as 5. And here, and if I were to add the same process here, it will product is already exists, so we cannot add the same process instead. And for the next arrival time, we will put as 1 and the first time of 3 at the process, and for the processing it automatically implemented, and for the development we put it as 2, the first time as 8, and the process new the time and 3, and the first time 6, just like in the report I do. And here I'm gonna run the simulation here, the execution file, and then just on the right here. And in here, the Gantt chart shows each process executing in level order, no preemption. And the matrix code on the right here update the average waiting time and the turnaround time in here. And now I can choose the status remaining time here and run the simulation again. And now notice that the Gantt chart is moving is more fragmented. P1 starts first but get preempted at tick 1, and when P2 arrives with the sorter bus, so the preemption logic works. And now for the job, I can also run my simulation, and it works. I get turnaround time and waiting time, and this is the Gantt chart. It runs 1 by 1. perfect one. So this two perfect from the for the first time. And next is the round robin. For the round robin, each person gets the two ticks at a time, and the game chart shows them rotating through the circular queue. There's only two here. And finally, they're also similar to the multi-level queue can run the simulator and it generates the execution timeline that is here. And I can also run the compare algorithms in here and just wait a little bit more for all the process to execute. And now it's finished, completed. I can compare the algorithm and you can see that the photos remaining time, it is the lowest waiting time and turnaround time for the response time. All FQ and all have the smallest, which means that it gets to the CPU first. And now for the terminal part, we can also put in here with this one, the CLI, you can now have the endpoints in here for console stuff, the default value in here, and you can see that the average time, turnaround time, and so on. Just to continue, I choose the option 2, continue, option 3, and option 4, continue for option 5. On the 6 comparison table, it runs one by one, and then you have the summary table in here. And for the 7, it is to change the input. Oh, sorry. Change the input and enter the number. For example, 0, is not 1, and process ID, this is not really the process was. Let's say 4, arrival time, let's say 5, and load time, 6, inventory, result is correct, so it's 8. Load from Unity, for example, I already have the file in here, and it's stored in here, so just copy and paste the file, continue, and then you can also load the JSON file, but it's all in run the version 6, yeah, updated. For the challenges, the biggest one for me was building the web interface, connecting the Flask algorithm files into the JavaScript functions one by one and getting the game out to render correctly in the browser took a lot of trials and errors. Another challenge was the MLFQ and aging logic, making sure that the process only moves up one queue level per tick and not tools. Overall, this project helped me to understand that each algorithm has its own disadvantage and there's no simple best one. It depends on what the system is made. And for example, SRT is best for minimizing the time quantum, and while the FLFQ is based on the response time and handling the time workload. Thank you.